Dear viewers, I Purvesh Nanavati welcome you to my channel Welding Education. Now in our previous class we have discussed about the weldability of low alloy steel. We have covered, we have talked about quench and tempered steel. Now I hope in this class I am going to speak about another low alloy steel, chromoly steel. And chromoly steel has plenty of use in the uh, petrochemicals and oil in refineries and application demanding high temperature corrosion strength and for sweet and sour service application. So chromoly steels were first developed in the 1920s, and over a period of time there have been many uh, development in the alloy to meet the requirement of the industry, like need to produce more oil means productivity and high temperature strength and material with good corrosion resistance and oxidation and creep resistance. So uh, depending on the service environment, whether sweet or sour, uh, and low sulfur and high sulfur content, 1 to 3 weight percentage chromium used for sweet crude oil low surface application, and 5 to 9 weight percentage chrome steel used for sour crude oil service application. And ASME code approves the chromoly steels for pressure vessel fabrication. Regarding development of chromoly steel, half chromoly steels used successfully up to 450 degrees Celsius, but they have low creep ductility, their tendency to graphitize, and predominantly ferritic structure. So having tendency to graphitize, the uh, strength drops and the structure is entirely ferritic structure. Next, 1 chrome half moly steel P11 T11 is with improved creep ductility, and the graphitization is eliminated with the development of alloy element. 2.25 chrome 1 moly steel P22 T22, higher oxidation resistance due to increased chromium, higher creep resistance due to increased molybdenum, and they're predominantly a banetic structure. So these banetic microstructures offer a very good oxidation and creep resistance, and the next they can be used in normalized condition and highest allowable temperature tensile strengths among low alloy steels. So 2.25 chrome monomole steels have been successfully used. Now regarding the development of advanced ferritic steels. So uh, in the work late in 1930s and 1940s, had demonstrated that alloying elutions or small additions of vanadium, titanium, columbium and other carbide forming have a potential strengthening effect on the strength of the material, particularly high temperature strength. So this successful introduction of X20 CrMo high carbon vanadium modified 12 chrome alloy in European countries and early 1966 were the early result of these efforts. So over a period of time, many advances were made in support of the nuclear industry's fast breeder reactor programs that began in the early 1970s, and these efforts were continuously made, and research worldwide made to the development of the modified 9 chrome 1 moly steels known as AS grade 91. So today P91 T91 is a very popular grade. P stands for the plate and T stands for the tubular structure. So this 9 chrome 1 moly and 9 chrome 1 moly vanadium steels, triple alloy steels, have now been extensively used for the application in power industries and petrochemicals and refineries and all that. So today we have P92 P911 ferritic steel with boron addition for boiler application and oxide dispersion strengthened alloys, and LAFMS for future nuclear application. LAFMS is low activation ferritic magnetic steel for nuclear application. Now in this slide we are going to uh, see the various alloys, the development of various alloys, particularly in the terms of 10 raised to 5 hours creep rupture strength at 600 degrees Celsius. The particular alloy exhibit different strength level, 35 starting from the 35 megapascal, like earlier 2.25 chrome 1 mole steel, 9 chrome 1 mole, 12 chromium. When they've been added with vanadium, molybdenum, vanadium, and niobium, some micro elements, they have been uh, strengthened and offered 60 megapascal. Then subsequently they have been alloyed, and they now latest they can be 180 megapascal. So this 12 chrome W cobalt nickel vanadium niobium alloy. So this is all about the alloy development, which result in the increased creep rupture strength. Now regarding the weldability fabrication aspects, these are susceptible to chrome steel, are susceptible to hydrogen assisted cracking and reheat cracking. Uh, Regarding reheat cracking, I'll be covering an entire lecture in near future, and slight susceptibility to solidification cracking. Solidification cracking aspects I'm going to touch upon in this slide only, in this presentation only. So poor toughness of weld metal produced with a welding process that uses a flux. So with this flux based process like SAW, the weld metal toughness is a concern. Then type 4 cracking is a, and second, hydrogen induces stress corrosion cracking, hydrogen attack and temper embrittlement, failure in dissimilar welds. So these are the various weldability issues with chrome steel. Now this table state recommends the minimum preheat temperature for welding chrome moly steels. So on the left side you see a various steel, half chrome half moly to 9 chrome 1 moly, and the second column, third column, fourth column showing the uh, various thickness range. So 30 mm, from between 30 mm to 25 mm, and more than 25 mm. The preheat temperatures, recommended preheat temperatures for in degree Celsius and degree Fahrenheit. Now the footnote A states that maximum carbon content of 0.15 with steel. For higher carbon content, the preheat temperature should be increased 100 degree Fahrenheit to 200 degree Fahrenheit. Lower preheat temperature may be used with the gas tungsten arc welding processes. Now about post-heating dehydrogenation treatment and intermediate stress relieving heat treatment, ISR. These three things are very much necessary to understand with respect to chrome steel. These are carried out during fabrication of the large component when immediate possibility treatment is not possible. So it has some purpose, and the purpose is, say, for post heating, heating the joint area for few hours even after welding is completed to assist the removal of hydrogen. Generally the temperature maintained is same as that of the preheating. So removal of hydrogen is the purpose, and the post heating is done for this. Dehydrogenation treatment, it is similar to post heating, but the temperature could be higher than what we uh, keep in post heating. It is typically 400 degrees Celsius. It has a similar purpose, removal of the hydrogen. And third is the intermediate stress relieving. This treatment is given especially when there is a long gap between welding and post-weld heat treatment, so that the ensure that residual stresses in the weld and hardness of the weld metal and heat effector zone are brought down. So when there is a sufficient gap between the welding operation and post-weld heat treatment, the ISR, intermediate stress relieving process, is highly recommended to ensure that whatever the residual stresses that were produced during the welding operation and the hard microstructure in the weld metal heat effector zone will be brought down, and properties become useful for the service application. Now effect of post heating DHT dehydrogenation treatment in